Okay, good. Let's get back to our discussions on the solving the linear system equation and system of linear equations. And as you can see here, we have, so we already talked about several methods. And the first one is the Gaussian animations methods. And the second one is the LU factorization methods. As you can see here, for the LU factorizations, as I mentioned last time, the L is the lower left triangular matrix, and it's used to record the Gaussian animations procedure. For the U matrix, that is the results matrix after the Gaussian animation. And for these factorizations, we get A can be decomposed into the product of L and U. And we show one example here to how to do the concrete detailed computation here. First of all, you need to create an L matrix, and then the L matrix is with all the ones on the diagonal and all the zeros on the above the diagonal. And for the elements here, and then it's just recording the ratios we have for the Gaussian animations process. And one thing I want to remind you of, so just warn you something about the ratio here. So PayPal's, a lot of students, they get used to do the Gaussian animations in this way, and then they would just use the, let me see. A lot of students just get used to the Gaussian animation in this way. You need to maybe plus something, and then plus to say, let's say +2 and then 1. And a lot of students, they get used to use the plus sign here, but what I recommend is to use each time you use the minus sign here, and then -2 and 1. And this makes clear that this one is the number you are going to fill out in the lower left matrix, the L matrix here. Some students, they just say, take a look at the ratio and then they fill out the 2 here, but this is not correct. We should have minus something, and then this something is the ratios we need to fill out in the matrix here. And this is the things. And it's really easy to get wrong for this entry here. Some students just write 1 here, and then because they write this operation here, E4 plus 1, and this is it's easy to get wrong. And so for this first column, and then it just record the ratios for the first round, and then this is second column, and then we have the second round ratio here, and then you will see this is the A32 divided by A22, and then it is just the 3 positions in this L matrix, the ratio. So what we have here, let me see, and I just write down the formula for the ratios here, and then you just need to fill out the ratio here for the matrix. But you need to pay attention here. This AJI it's not just the number in the original matrix. It should be, so for each round, and for the round 1, the number here is from the original matrix. But for the round 2, the number should be from this matrix. This is the results of the round 1. So this is not just all the numbers from the original matrix. If I want to write it with a correct notation, so for example, this is the A. Let's say this is the original matrix and this is the A1. If I want to write it with the correct things,
and then this is the A1. And this is the results in the up to the round 1, and then we call it A2. And this is the A3. So if I want to write it with a correct one, the correct number, and then it should be the, let me see, this is the I column. So, and also we have the I matrix. So I use a superscript here, which means that this number, so for example, this one, it should be coming from the first matrix, and then it's the A21 and the A11 in the first matrix. And so this is the first column's value, and then for the second column value, and then you substitute the second column, and then that is, it means that the I equals to 2. And for example, here we have the A32, the 32 precision here, and then that is R32, and then here is the A32, but it's from the second matrix because I equals to 2 here. So I just give you the one example. For example, the R232 here, R32, and then it equals to A32, and then from the second matrix, and the A22 from the second matrix. The superscript is denoting the matrix we are using, and then because it's from the second matrix, and then A32 position is this, and then divided by A22 from the second matrix, and that is the -4 divided by -1. And so this is the equals to 4. So this is something you need to pay attention to. The first thing is that try to write the minus signs every time, and then take the ratios and then write them the ratios to the corresponding place. And another thing when you need to pay attention is when you write the ratio here, this number, it should be from the corresponding matrix. And this is all the things. When you have the LU factorization, so we mentioned this last time. And when you have the LU factorization matrix, we are going to solve the linear systems with 2 steps. So this is the first, this is the LU factorization, and we plug in the A here, and then we get LU times X, and then E equals to B. And because this is the matrix vector multiplication, and then which means that we can do the associative law, and then we can do the multiplication for U and X first. And then the UX, we let the UX equals to Y. And then because this part, we let it to be Y, and then we have LY equals to B. And so now we solve this equation first, and then because this is a lower left equations, a lower left system, and then we can solve from the top to the bottom, and this is called forward procedure. And then we solve for the Y for this system, and then once we get the Y, and then we substitute back to the Y back to the system of linear equation, and we solve for the X. And then for this one, upper right, so which means that we are going to solve from the bottom to the left, to the top. And you will see we will solve we will first solve the angle here. So there's the less confusion here. So we solve from the bottom to the top. And this is the methods LU factorizations. Any questions so far? How the procedure look like? And so this is some things we talked about last time. And then we also mentioned that from the LU factorizations derivation, this is the basic version. Of course, you have more advanced versions later on. But these derivations on the textbooks, I skip the derivations part because it's long and boring for the students. But if you are interested in the derivation part, you can definitely go to take a look at how to derive the LU factorizations. It's 2 pages long on the textbook. But in the derivations, the textbook has assumed one things about the matrix of the system. The assumptions is here. We can perform the Gaussian animations without row exchange. And this assumption, as I mentioned last time, if you haven't gone through all this process, the Gaussian animations process, and then you don't know beforehand if we need a row exchange. So this criterion, it seems not useful. So what we have here is more useful. And this thing is just stating that we can perform the Gaussian animations without row exchange, but we have some criteria to decide whether this happens. So this is the criterion, M by M matrix. And the second criterion is leading principal submatrix A1 AN, A1 A2 A to the AN are all non-singular. And then A has your every factorization, and then the factorization is unique. And this is some things I want to mention today. Talk about this theorem, not the proof. It's just about the statement. Lucky you don't need to prove anything, because I don't like to get you into 1 hour proof in the final sem. Just prove one theorem. That's too horrible. And but it could be if you continue to take some mathematics classes, advanced mathematics classes, and then you will have some maybe a proof, and then it takes like 1 hour to prove it in your exam, and then you have a 3 hour final exam time. So let's get to take a look at the statement, and then just focus on the statement. There are several definitions here. First is the leading principal submatrix, and then the second one is the non-singular. So first, I'm going to give you the non-singular, the leading principal submatrix. So this is the definition. To understand this theorem, there's the definitions of the leading principal submatrix. And so let's see. So here we have the matrix. So first we have the matrix A, and then I'm going to use the Aij to denote the element here. And then this is an M by M matrix. Now, what is the leading principal submatrix? So its leading principal submatrix is quite simple. The definitions, the submatrix are the square matrix looks like this. So the leading principal submatrix on the left top. So here we have the subscript here, AK, and then we have A11, and then to the A1K, and AK1 to the AKK. And this is the K submatrix. And then the K can be 1 to the N. And this is this definition is very simple. If you take a look at the A matrix, and then this is the A1, right? Because we have just the A11 here. And then this one is just the A11, the A1 submatrix. And for the, let me just write more element here, what A12, A21, A22. And for this one, this top left, the left part at the top, here, this one is the A2. This part is the A2. So and so forth, you have the A3 here, A13, A23, A33, A32, A31, and this is your A3 submatrix. And so for an n by n matrix, and then you have n submatrix A1 to the AN. And the AN is just itself. And this is the definition of submatrix, leading principal submatrix. Let's see. So I'm not going to give you the definition of a non-singular, but one criterion for the non-singular is criterion for non-singular matrix or non-singular. Matrix, one time criterion is that, so we can determine the determinant of the matrix. Let's say this is the M matrix, and then it does not equal 0, and then this is, and then we can say this one is M is non-singular. Or if the M matrix is non-singular, and then we can say the determinant of the matrix does not equals to 0. And this is one criterion for the non-singular matrix. So now there's another way to decide it, of course. So later on, we will take a look at other criterion to see if the matrix is the LU factorizations. We can perform the LU factorizations. So this is the one criterion here. We have the principals of matrix are all non-singular, and which means that the A1 to the AN are all non-singular. Then we have the conclusion that LU factorizations, we have the LU factorizations for the A, and the factorizations is unique. This is the things. So which also means that, so this means that for this number, for this submatrix here, so the first one, determinant of the A1 does not equal 0, which means that A11 does not equal to 0, right? And then the A2 is also non-zero, and then which means that the determinant of the small part is non-zero, and then the A3 determinant of the A3 is also non-zero. And so we have all these determinants of the leading principal submatrix non-zero here. And the next, so I'm going to give you one corollary here. So first, before we move to the corollary, I'm going to introduce one thing. Here is the, let me see. So I'm going to introduce some things that is previous before this chapter, and then we are going to make use of this theorem and definitions to get a easy version of this theorem. So first, this one, the definition is, so this is the definition here, definitions of the strictly diagonal because you can see for this version of the theorem, and then you need to calculate the determinant of M matrix, and then it's quite computational expensive. But sometimes the matrix, it seems that it has a very good pattern, and then it is called a strictly diagonal matrix. And this is the definition of it. And so for another, so now we have an n by n matrix again, n by n matrix A. It's with the entries Aij. And the I equals to, so we have n entry, n by n entry here.
So the A, I, and J can be 1 to the n. So if this matrix satisfies the following things, and then we call it strictly diagonal. And it's super easy. The criterion here is the AII for each row. This is for each row. And then AII is bigger than the absolute value of the diagonal element is bigger than the sum j equals to 1 to the n, but the j does not equals to I. And then the summations here, and then taking the absolute value of AIJ. And for I equals to 1 to the n. And this is the definition of strictly diagonal matrix, diagonally dominant matrix. Let me see. Let me give you one examples for this one. Do I have one concrete examples for the LU? Let me see. I don't have one example on the lecture notes, but I can create one for you. So now I'm going to create one such an matrix here. It's quite easy to create it. It's 4, 3, and then 6. And then -1, -2, -2, negative. Let me see. I cannot have negative things here. Negative maybe 0.5, and then 2, and then 3. And this matrix is strictly diagonal matrix. Maybe there's some things missing here. It should be strictly diagonal dominant. Dominant. And if you take a look at each row, so for the first row, and then your diagonal element is 4, and we have 4, and then it's bigger than, take the absolute value, and then it's bigger than the rest of the sum of the rest of the elements with the absolute value sign. So which means that it's bigger than -1, and then plus the -2. And you check this, and then this is actually happened. The diagonal element is bigger than the sum of the rest of the element in the same row, and with the absolute sign. So for the second row, and then we are going to try the same thing. This is the diagonal element, and then we take the sum of the absolute value of the rest of the element. And then it's always said this is strictly bigger than the right-hand side. And once again, we focus on the diagonal elements on this third row. And this one is bigger than the rest of the elements in the same row, the sum of them, and as the sum of the absolute value of them. And then so we can conclude that, A is strictly diagonal dominant. Strictly diagonal dominant. So it's so quite obvious that from the name, and then you will see that. So for the strict, and then we have the bigger than side, but there's no equal side. And diagonal dominant, and then which means that we put the diagonal element here, and that is dominated the rest of this element in the same row. And this is the definition of a strictly diagonal dominant. And I'm going to give you one example here to test if this matrix is a strictly diagonal dominant. So all the things are the same here. And then, but now I got this, the third row. So is this strictly diagonal dominant? No, I can say some shaking head here. And it's not, because the last row we have the 6, but we need to be very careful here, and then we need to put the absolute value sign and then plus the absolute value side of the second element in the same row. And but here the 6 equals to the diagonal elements equals to the sum of the rest of the elements, the absolute value of the rest of the element. So A is not the strictly diagonal elements matrix here. It's not strictly diagonal dominant. And this is how we get there. We decide how the whether it is strictly diagonal or not. And this is the example. And let me see. So there's one more thing. There's some things here, and then I'm going to write down a corollary. It's about the LU factorizations. So the corollary here, corollary is the 9.5, and then from that definitions, and then we already know there's some things here in the theorems. It's about the strictly diagonal dominant. So let the A be an m by n matrix, and then A equals to LU, that is factorizations, and then L is the lower triangular matrix, and the this one is the upper triangular matrix. And the L, we have some requirement restriction here with the ones on the diagonal. And this is how we calculate the L before. So then LA has the LU factorizations if either the either these two situations. So either this two situation is satisfied, and then we have the LU factorization. This is two special situations in the theorems here. So this is theorem 9.1. It's the most general case. And then for the corollary, it's just some special cases. And then the first cases is the A is strictly diagonal dominant. Strictly diagonal dominant. This is the first special case. And then the second special case is some things you are familiar with. It's symmetric. And then positive definite. A lot of the time, the students would get confused. Should I find out a matrix that both satisfy this criteria or not? Because this is either it means that you can satisfy either this criterion or this criterion, and then we would have LU factorizations for the A matrix. And you will see this one is they are asking about different things about the A. So this one is the diagonal dominant, and this one you need the symmetric. But here for the A situation, you don't need the symmetric things. And this one also requires the A to be positive definite. And they are different criterions. And then if the matrix satisfies either one of these, and then we can say the A has the LU factorizations. So there's some transitions between the theorems 9.1 to this corollary, and there's the transitions here, and this is something we in the previous chapter, but it's not in the Math 104B or 104A class, but I'm going to mention here. So from the transitions, so here from the theorem 9.1 and then to the corollary 9.4, actually we use the following theorems here. So the first one is the theorem 8.1 in the textbooks. So let the A be a symmetric n by n matrix, and A is positive definite if and only if the determinant AK is always bigger than 0. It's always positive for the K equals to 1 to n. And this means that for matrix A is positive definite, then you have the determinant of all the leading principal submatrix. The determinant of them are always positive. And if you compare to what we have in the theorem 9.1, so let's see, compare it to what we have in the theorem 9.1, we just need this one, we just need the determinant. This one is just the A determinant of the AK does not equal to 0, right? So, but now, if the matrix is positive definite, and now we have the determinant of all this leading principal submatrix is positive. Positive, it also means that this determinant does not equal to 0, right? It's non-zero. So this satisfies this criterion here, which means that all the positive definite matrix, it has LU factorizations, and the factorization is unique. Does it make sense? The logic here. So that's because, and then let me repeat this, because the positive definite matrix has the determinant of the leading principal submatrix. The determinant of the leading principal submatrix are positive, and positive, it also means that does not equal to 0, right? So this satisfies the criterion we have for the in the 9.1, and then which means that our positive definite matrix has LU factorization, and then we have this conclusion here because the positive definite matrix satisfies this criterion here. And this is one, the second one. So this gives us, so this is the theorem 8.1, and then the theorem 9.1, and then we combine them, and then we only get so this one, we combine them, and then combine the 9.1 and 8.1 theorem, and then we get the B part in the corollary 9.4, and then let me just write down here. These are the special case. So don't mess. Don't don't mix the corollary 9.4 and then the theorem and with the theorem 9.1. Theorem 9.1 is the most general cases, and then the corollary 9.4 is just some. They are just some special cases here, and we just finished the with combined the theorem 8.1 and the theorem 9.1, and then get the B part. And let's see the A part. How can we get the A part? So we need one theorem here to help us to decide the A matrix. If the A matrix is strictly diagonal dominant, then it satisfies the criterion in the theorem 9.1. And actually, we have such a theorems on the textbook, but we are not going to prove it. And then this is the theorems in the chapter 3, and then it's the theorem 3.6. And then so let the A to be a strictly strictly diagonally dominant matrix, there's some things about this. Then the A is not singular. And how can we use this to get the corollary 9.4a? So first, this is the theorem 3.6, and then we want to see, we want the determinant AK does not equal 0 for the A. For all the leading principles here. This is the criterions in the this is the criterion in the theorem 9.1. This is the criterion from the theorem 9.1. So how can we go from the theorem 3.6 and then to this go from the theorem 3.6 to this condition here in the theorem 9.4, and we want to prove that strictly diagonally dominant matrix, and then it satisfies this criteria. So this is really simple because it's a strictly diagonal dominant matrix, which means that for each row you have, so let's see. So for each row you have, let's go back to the definition of the strictly diagonal dominant, right? And it's just AII, the diagonal things. And then it's bigger than the sigma sum J equals to 1 and the N, right? And then J does not equals to I and then AIJ. So if you just focus yourself on the sub matrix, for examples, let's focus on the AK, okay? And it said the AK, this leading principles matrix, so is this AK a strictly diagonal matrix? And why do I ask these questions? If this is the AK is the strictly diagonally dominant matrix, if AK is such a matrix, is the strictly diagonal matrix, what can we have? We would have, so from the theorem 3.6, and then we can say the determinant of the AK does not equal 0 because the AK is non-singular from the theorems 3.6. Does it make sense? So if the AK is a strictly diagonal dominant matrix, and then from the theorem 3.6, and then let's replace the A with the AK, and then the AK is non-singular. So this is what we want. So here the question is that if the A is strictly diagonal dominant, and then it said the AK a dominant, strictly diagonal dominant matrix. This is the top left, the K by K matrix. The top square here, the square on the top left. So why, if it is, and then why? So this is the K by K, right? This is the K by K. And this is the definitions for the A, and then the I is from the 1 to the N. So if we want to check, so this is, let us think about this. We want to check the AK is a strictly diagonal dominant, and what we need to do is to check AII is bigger than, so AK, what's the dimension of the AK? It is K by K, right? This is a K by K matrix. And so now, instead of checking the dimensions N, we are going to check J equals to 1 to the K. And then j does not equals to I, and then aij, and we check row by row, and then we just need to check the first k row, right? So does this happen? Does this condition hold? Yes, actually you have this, because from the, this is from the A is strictly diagonal. A is strictly diagonal dominant. And this is from the definition of this dominant. And then we have the purple part. So this is from the definitions. And then now we want to prove that the AK is the strictly diagonal dominant. So let's see, from the A definitions we already have. So I'm going to just do the copy and paste here. So from the strictly, A is strictly diagonally dominant. And then we have this. So from the A is strictly dominant, diagonal dominant, and then we have this. And we have the calculation here, AII, and it's bigger than the N, J equals to 1, J does not equals to I, AIJ. And one important thing is here is the absolute value. So which means that it's bigger than or equals to, we can drop some ton here, and then we just add to the K, and then J does not equals to I. So this proves what we want. AII, the absolute value, is bigger than the sigma sums J equals to 1, and then to the K, J does not equals to I, and AIJ. And this proves that the AK is strictly diagonal dominant. Does it make sense? We just take part of it, and then we get the AK is strictly diagonal dominant. And once we have, we know that the AK is strictly diagonal dominant, and then we from the Theorem 3.6, we know that the AK is non-singular. And this is what we have in the Theorem 9.4 criterion. We want all the principles, leading principles matrix are all non-singular. And this proves that if A is a strictly diagonal dominant things, and then we have the LU factorizations for it. And so the theorems, so here I'm just conclude that the Theorem 9.1 and then combine with the Theorem 3.6, and then we can get to the A part, the A in the corollary 9.4. Does it make sense? So this is a transitions between the theorem and the corollary. And once again, I want to remind you of the difference between the corollary and the theorem. The theorem are the most general cases. And sometimes you can find out the some cases. So there are cases that satisfy this criterion, but it does not satisfy the criterion in the corollary. The both cases does not satisfy the. So there's some cases that does not satisfy all the criterion in the corollary here, but it satisfies the criterion in the Theorem 9.1, and those matrices still have LU factorization. Does that make sense? This one is the most general case, and then the corollary, just two special cases. And this is a difference between them. Now, one more thing I want to mention about the LU factorizations. This is a very special case we have. So
the intuitive sense of this all these theorems or all this corollary is about the Gaussian animations without row exchange. But now, what happened if we need to do some row exchange? If we need to do some row exchange to get to the Gaussian animations without the right triangular part, then actually we have a more general part or general version of the factorization theorem, and it's just about the non-singular matrix, more general cases. So this one we have, so for any non-singular matrix A, there is a permutations matrix P. So for this permutations matrix, and then we are going to change the, so there's a permutations matrix P, then the matrix P multiplied by A, and then can be factorized into the PA and then times LU. That is the LU factorization here. So there's one more part here about these things is the permutations matrix. But now you will see the criterion is quite general because it's just for the non-singular matrix. And what is the permutations matrix P? So let's go back to the things we have here. Let me see. We don't have the things here, but for the Gaussian animation matrix, you have some permutations in between, right? In the step 2 and then step 3. Do you remember that? Before you do the actual row animation, and then you have the step 2 and the step 3 to choose the correct row and then do some row exchange there. And actually in matrix linear algebra, you can express this row exchange things, row permutation things by a matrix. And then, so for example, if you are going to exchange a row 1 and a row 2 here, there's a row 1 and a row 2 and a row 3. And let's say this is a 3 by 3 matrix. And if we want to exchange the things here to row 2 and a row 1 and a row 3, and it's actually doing some matrix modification here. And let's say I'm going to change the row 1, right? And then row 2, 0, 0, 0, 0. And then this is the identity matrix. And then this is the matrix A. Times the matrix A. And then now we will get to, by this matrix, you can see I just changed the, maybe just the identity. So this is the identity matrix, but I switched the row 1 and row 2. And if you do the modifications to this matrix, and then it's the same as this one. So this is the permutations matrix. You just switch the row here in the identity matrix, and then this is the permutation. So what it's saying here is that, so instead of doing the row exchange during the Gaussian eliminations process, suppose you know the row exchange beforehand, and then you do the row exchange at one time, or the row exchange at one time, and then do the row exchange first, so that when you do the Gaussian animation process, you don't need to do the row exchange. And this is the theorem, this most general case. We do the row exchange first, the permutation matrix here, And then this result here, this matrix result here, we don't need to perform any row exchange here for this result matrix during the Gaussian animation, so that we can have every factorizations for it. So this is the most general case. This is for any non-singular matrix A, but this is a more advanced topic, and then it will not be on the exam. So this is all the things we want to mention today, and the next time we are going to talk about the Kolesky factorizations. And these theorems are some things you need to memorize. The theorem 9.1, just the 9.1 and corollary 9.4. And this is some things you need to memorize, and you need to apply to some concrete examples to determine whether you have a LU factorization, the basic case. Bye.